top left. Yes,
Yeah,
sir. It's now recording.
it is. Yeah, okay, fine.
So now you can continue. Thank you, sir.
Yeah. So I guess the screen is visible. Okay. Is the screen visible?
Yes, sir.
Hello?
It's visible.
Yes, sir, it's visible.
Okay, okay. So the yesterday we started the discussion on the volatility models. We have noted that volatility is an unobservable phenomenon that has to be modeled. But how it should be modeled, it all depends on the kind of approach that we adopt. The most simplistic thing is to have the historical volatility. That is, you compute the variances or standard deviations based on the data. Okay. When you calculate standard deviation for a particular period, you get only one single number on the basis of which it's not possible to observe the variations. So therefore you need multiple observations. So which means following the same approach, you calculate standard deviations based on a rolling window. Arbitrarily fix a window length, let us say 10 observations or 8 observations, roll it through across the entire sample, then you have multiple measures of the standard deviations. You plot them. If small sigma t represents the standard deviation, plot it against time, then you see the variations. So these variations would reflect possible presence of volatility based on historical data. The other approach, which we started discussing yesterday, was the conditional volatility. That is where the arch-gauge type of models are located, which anyway we will be discussing now in greater detail. The next approach is the stochastic volatility. It is just an extension of the conditional mean approach in the sense that you introduce an additional stochastic term into the model. And the last one is the implied volatility, which is more relevant in the context of the derivatives market. So, of these four approaches, our focus would be exclusively on the conditional variance volatility models, that is, the arch and gauge models. As a starting point, we now formulate an arch model. In any of these models, the family of arch-gauge models, please note that there are two important components which are represented by two equations. The first equation is the mean equation. And the second equation is conditional variance equation. Okay. Now, the mean equation is specified as, in a simplest form, let us say, if yt is the process, this is specified as mu, which is nothing but the conditional mean of y, and an innovation in yt represented by epsilon t. This is the simplest form of the mean equation. It is possible that we can generalize the mean equation in many ways. For example, this yt could be a times yt minus 1 plus epsilon t. So this is simply the autoregressive kind of models. In general, we may write this as some function a, that is a polynomial a, in backshift operator b yt minus 1 plus epsilon t. Okay. So if this polynomial is of first degree, then it will be of this form. But you can as well have the autoregressive dependence spanning across higher lags like lag 2, 3, 4, etc. But these are somewhat more complicated. So to introduce the mean equation, the simplest form is this, that yt equals mu plus epsilon t. Okay. Now, in this, yt equals mu plus epsilon t, right? If you take expectations, expectation of yt, conditional upon all the available information up to time t minus 1, which you may write as yt minus 1, yt minus 2, etc. Okay, this is conditional expectation. This is nothing but expectation of mu. Since mu is constant, that is mu itself plus expectation of epsilon t, again conditional upon the whole information set yt minus 1 dot dot etc. Okay. So this anyway is 0 because by assumption the innovation in yt, that is epsilon t, is assumed to be of mean 0 type, then it is mu. So mu is therefore the conditional mean. Then if you take yt minus mu, this is your epsilon t. And yt minus mu whole square is sigma square. And take expectations on both sides. Again, conditional expectation. This whole information set, you may call it as given psi t minus 1, just for the sake of brevity. Again, you write expectation of, again conditional upon psi t minus 1. Okay, so you call this as sigma square t. Okay, so the variance of yt is the same as the variance of its innovation, that is epsilon t, which we designate it as sigma square t. Okay, is this clear so far? Hello?
Yes, sir. So could you just scroll
Yes,
up
sir.
once?
Pardon?
Could you just scroll up once on the notes?
Up or down?
So I want to see what was written earlier.
This is what was written earlier. Okay,
Thank you, sir.
this same thing I have written again here. Okay, so please note that the variance of yt is the same as the variance of epsilon t, which is nothing but its innovation. But in Archgard formulations, we make another important implicit assumption, that is, epsilon t equals ut and sigma t. So here, sigma t is already defined. You take the root of this, that is nothing but sigma t. But this symbol is to be defined. So this is N01, a standard normal variant. Okay. Now take squares on both sides. Sigma square equals ut square, then sigma square. Okay. Now take conditional expectations on both sides. Expectation of conditional upon the information set. This is nothing but sigma square t. Expectation of this is itself, because this is not a random variable. Okay. Once it is computed, it becomes a non-random variable. And expectation of ut square, expectation of ut square, again conditional upon the information set. This is nothing but unity, that is 1. Why? Because of this assumption, right? So therefore, sigma square, expectation of epsilon square, this is nothing but sigma square, and this is 1. This is sigma square t, right? This is what we have. So this is assumed to facilitate this. That is, the conditional error variance is sigma square t, and sigma t is nothing but the standard deviation of epsilon t, which is the same as yt. Okay. So with this clarity, we now move to what is known as the conditional variance equation. This is our second equation. Okay. So what is this actually? Sigma square t? It's nothing but conditional variance, right? So sigma square t, okay. Now the question is how it evolves, how the sigma square t evolves, okay. So sigma square t evolves, let us say in this fashion, omega plus summation I equals 1 to q alpha I t minus I square. Okay. So let us call this as equation 1. And the previous equation, that is this one, the mean equation, as you may call it as 1 prime. This is 1 prime. The conditional variance equation is 1. And the conditional variance equation may also be written in compact form like this, equals omega plus alpha b. This alpha b is nothing but a polynomial in b, and b is the backshift operator. I think this notation must be familiar to all of you. This is t minus 1 square. We call this as equation 2. Equation 2. Actually, 1 and 2 are the same. Only thing is they are differently represented. 2 is nothing but the short form of 1. And here alpha b is polynomial in the backshift operator b. Okay. Now, sigma square t, what is it? It is conditional variance. Technically, it is variance. Can variance be negative? No. So sigma square t should be positive. Should be positive. Okay. If this is to be positive, okay, then what restrictions are need to be improved on the parameters in equation 1? It is essential that omega should be positive, alpha 1 should be positive, dot dot dot, alpha q should be positive. Positive. Okay. So this is what is known as the positivity restriction. Okay. Now let us define another error which may be called as VT. Let us define as VT. Okay. So let VT is the forecast error. What is VT? Forecast error while predicting sigma t square. Okay. So therefore, Vt should be equal to sigma t square, because this is actual, minus its expected value, that is t square, conditional upon the information set. Okay. So if you recall, this is nothing but your sigma square. So sigma minus, this is nothing but sigma t square. Okay. So this you substitute in the conditional variance equation. Okay. So by doing so, that is, you try to eliminate sigma square t and bring in epsilon square by using this. That means simply, right, bring it sigma square this side. Alternatively, sigma square t equals epsilon t square minus Vt. Okay. So on the left-hand side of the previous equation, you substitute this. And when you rewrite, you get equals omega plus beta t minus 1 square plus Vt. You may call this as equation 3. Call this as equation 3. Okay. So if you look at equation 3, are you able to grasp anything? Is this an AR process? Is this an AR process? Yes. It is an AR process. But what is the variable here in the AR process? Sigma t square is the variable. And this is nothing but an AR process. What is the order of this? The order of this polynomial is Q. How it is Q? You take the summation here, I equal to 1 to Q, right? So from this, it follows that equation 3 corresponds to an ARQ model. Equation 3 is an ARQ model In which variable? R cube model in. This model refers to what? Which variable? Hello? I have written there epsilon t square. Okay? Hello?
Yes, sir.
Yes, sir.
Yeah. Okay. So this is also for about the conditional variance. You can also compute the unconditional variance. So the conditional variance is time varying. That is, this one is time varying. That is why we had put the suffix t. Whereas the unconditional variance, if you compute variance of epsilon t square, unconditional variance, you get the expression omega upon 1 minus alpha 1 minus alpha 2 dot dot minus alpha q. Okay. So these epsilon t's are serially uncorrelated, but they are not necessarily independent through time. Right? Shall I proceed further? So this is the
Yes,
general.
sir.
Could you repeat that last unconditional variance bit?
No, I will work out some steps so that the concept of conditional and unconditional variances would get clarified. Okay? This is an important thing and it needs some further. I will do that now. Okay? Now, for this, let us take a simple model where q equal to 1 for simplicity's sake. So when q equal to 1, then the model becomes arch 1. Arch q becomes arch 1 model. Okay. So let, as usual, we write yt equals mu plus epsilon t. Okay. And what is epsilon t? Epsilon t is nothing but ut. We have written as sigma t. Sigma t. And what is sigma t? If you recall the previous step, this is nothing but ut. Okay. And sigma t square is nothing but omega plus alpha sigma square t minus 1. This is actually the ones inside the parenthesis is sigma square t. Since it is sigma t, you take the square root of this. Square root of this. Okay. So let me write this little more clearly. This epsilon t can be written as ut multiplied by omega plus alpha. We are not writing alpha 1, alpha 2 because all the alphas, they collapse into only one. That I am calling it as alpha. Okay. Alpha epsilon t minus 1 square root of this, because this is sigma t. Okay. Now, what is the restriction that we have imposed on this? It is over. Okay. What are the restrictions that we imposed earlier, if you recall? And what was the assumption that we made with regard to ut? Come on, follow it up. Ut follows.
Normal 0, 1.
Yeah. In addition, IID, like independent and identically distributed normal 0, 1, without any loss of generality. We assume like this, right? And what about omega? Should it be positive? Yes. Why? Because the conditional variance should be non-negative. And by similar logic, alpha should also be positive. Okay. So now, here the expression omega plus alpha epsilon t minus 1 square, right? Whole the square root of this. What is this? This is nothing but the standard deviation. Standard deviation of what? One moment. Class లో ఉన్నాను 4:30 తర్వాత. Sorry, some interruption was there. So this is standard deviation of what? Hello? Standard deviation of epsilon t. Okay. So this is what kind of standard deviation? Can you qualify this?
Conditional, sir.
Yes, conditional standard deviation of epsilon t, right? So now the conditional expectation of epsilon t is 0. Let us prove that expectation of epsilon t conditional upon the information set t minus 1 equals, okay, expectation of ut conditional upon the information set ut minus 1 multiplied by omega plus alpha epsilon t minus 1 square. Okay. What about this term? This is 0. And therefore the whole thing is 0. Hence this statement. The conditional expectation of epsilon t is 0. And the conditional variance, which we have already worked out, it is a repetition, but better to do that. Conditional variance of epsilon t is given by, okay, so variance of epsilon t given the information set t minus 1, okay, this equals expectation of epsilon t square. You have to again subtract from its mean. Since mean value is 0, you don't need to do that. Information set t minus 1, okay. This is nothing but expectation of ut square, again conditional upon the information set ut minus 1. Then you also need to square this. Okay. In the previous step, sorry, here you have to put. When you square that, then this simply becomes omega plus alpha sigma square t minus 1. And how much is this? This factor is nothing but unity by assumption. Then it simply becomes alpha epsilon t minus 1 square. So this is what we have shown earlier. So this is nothing but your sigma t square. That is the conditional variance of epsilon t. Also yt is simply this, right? So the conditional mean therefore of yt, okay? What about yt? The conditional mean of yt mean of yt, okay? Now work it out. What is yt? Yt is mu plus epsilon t, okay? Now take expectations on both sides conditionally. Yt psi t minus 1. This is mu itself plus expectation of this conditional upon psi t minus 1. This anyway will be 0.
0.
So therefore this is mu itself, right? Now work out the conditional variance of yt and check whether is the same as the conditional variance of epsilon t given the information set. Actually here psi t minus 1 is nothing but yt minus 1 because we have only q equal to 1 because this is only an arch 1 process. But anyway, let us write in general terms. This is nothing but expectation of first principles yt minus expectation of yt given yt minus 1. This is nothing but mean and square this. By definition, this is variance of yt. Okay. So if you simplify this, this simply becomes omega plus alpha epsilon t minus 1 square. This is nothing but your sigma square t. This is also the same as the conditional variance of epsilon t given the information. Okay. Now let us finally write that the conditional variance of, now from this what do you observe? The conditional variance of yt, okay? Is it time varying? That is sigma square t is, this is more important actually, all of you are very silent. This is time varying. Is this clear?
Yes, sir.
Yeah.
Yes, sir.
Now what about the unconditional part? Because all of you must learn how to compute the unconditional part also.
So could you just give us 1 minute to write everything down?
Yeah, sure.
Thank you.
Are you through?
Yes, sir.
Yeah, okay. So next is unconditional. Unconditional mean and variance. Variance of yt. Okay. Now yt equals mu plus epsilon t. Okay. So now expectation of yt, we are not putting any condition here. This is unconditional mean. Expectation of mu plus expectation of epsilon t. What about expectation of epsilon t? This is 0. And expectation of mu is mu itself. So therefore the unconditional mean of yt is mu itself. Whereas the variance, unconditional variance of yt equals variance of epsilon t. Variance of yt, because mu, the variance of mu is 0 because this is constant. So the variance of yt is the same as variance of epsilon t. And what is variance of epsilon t? This is expectation of epsilon t square. Okay. And what is epsilon t? Epsilon t is nothing but ut sigma t. Okay. By assumption. So if you substitute, you get expectation of ut square unconditional omega plus alpha epsilon t minus 1 square. Okay. So this is nothing but omega plus, this is unity. This is nothing but 1. And this will be omega plus alpha into variance of epsilon. Okay. So variance of yt, the variance of yt is the same as is variance of epsilon t. Okay. So by rearranging the terms, you get variance of yt is nothing but omega upon 1 minus alpha. Just you rearrange the terms for alpha less than 1. Okay. This is for a stationary process. Okay. So you can see that there is, these two are not one and the same. Okay. So now let us, before we proceed further, yesterday someone was asking, what is arch test? It's an important test. Arch test. Okay. As a preliminary step, we have to ensure that there is arch effect in the process or in the data that is given to us. Only then it makes any sense to proceed further. When there is no arch effect, then modeling the same using arch has no meaning. So therefore, how to confirm that there is arch effect? Okay. So this is done with the help of a test known as LM test. LM test. So this test is due to Engel, 1982. Okay. So this test is, the formal test is as follows. let yt equals p1 yt minus 1 plus dot dot p of p yt minus p plus epsilon
sir,
t. Yeah,
so you mentioned that LM test is a way of detecting the arch effect,
yeah.
correct? But sir, could you please tell us what exactly is the arch effect that the model is trying to detect?
See, arch effect means the presence of volatility, some form of volatility. Okay. First, you have to confirm whether there is volatility dependence among the errors, right? If there is no such dependence, then there is no arch effect, which means you don't have to do arch modeling, arch or arch modeling.
So, sir,
Okay.
isn't it expected that most time series data will have differing uh, differing
Volatility.
volatility? But here, what they're trying to do is trying to figure out if the volatility and if the x are dependent on one another. Is that what they're trying to do?
Yeah, let me put, yeah, idea is the same. See, it is expected that most of the financial time series have some form of volatility, agreed. But how can you take that statement as a financial econometrician? You need to confirm that, isn't it? So to confirm that, you have to subject the data to a test. All right? That is what we are discussing.
Okay, sir.
Yeah. So let the process be given by yt equals p1 yt minus 1 plus dot dot p of p yt minus p plus epsilon. So can you recognize this part? This part? What
This
is
is the
this actually?
AR
Yes, yes. So yt is an ARP process.
without an
ARP.
intercept term.
Yeah, yeah, with or without. Yes, of course, here there is no intercept term. Okay. So this is an ARP process. And what was the assumption that is generally made about epsilon?
That it is
Is
a
a
white noise.
white noise. Okay. Sometimes the white noise could be, additionally, it can also follow the Gaussian process. That is normal process. Whatever it is, okay, it is white noise, sigma square, epsilon. Okay. Now, if there is arch effect, okay, then what is the null hypothesis here? The null hypothesis is that there is no arch. There is no arch. And the alternate hypothesis is that this is arch Q. Arch Q. So for arch Q, you have to extract the residuals. So to extract the residuals, you run a regression of this. Regress yt on yt minus 1 up to yt minus q. Okay. So, but where do you get this epsilon hat? So extract the following steps. Run, this is your alternative hypothesis, H1. For that, step 1, run a regression of yt on past yt as given here. That is step 1. So from step 1, you get the output epsilon t hat. This is the output. Will you not get this? Extract epsilon t hat. Okay? Hello? Any of you?
Sir, I think what they're trying to do is they'll first create a model and
Yeah.
they'll extract the error terms. Then they'll
Mhm.
regress the error terms either on y or on x to see if there's any.
No. Step
Okay.
1 is run a regression as shown here. Regress yt on past yt like this. Up to what lags? P lags. Okay? That is step 1. What is the output that you get from step 1? Epsilon t hat. What is epsilon t hat? Residual from the regression. Hello? Residual. Step 2, square the residuals. That is, square the residuals. Okay? Then replace yt by epsilon t hat square. And this as epsilon t minus 1 hat square like that. Okay? Step 2, run the regression. Okay. What is happening? Then run the following regression. Epsilon t hat square equals, use different coefficients, alpha 1, sigma t1 hat square, dot, alpha p, sigma hat square, t minus p, less some error eta t. So run this regression. So after regression, under H naught, okay, what is required if you want to accept H naught? Alpha 1 equal to alpha.
All equal to 0.
Yeah. If it is arch Q, then put this as Q equal to 0. Okay. So for this, the relevant test statistic is T is the sample size, R square which you get from the regression, TR square follows chi-square distribution with Q degrees of freedom. Okay, where T is the number of observations. Okay. Based on this TR square statistic, if you are able to reject H naught, then you confirm that there is arch effect. Arch Q, that is arch effect is present. So then you proceed towards modeling the series. Okay.
So could you? I'm a little confused. What is TR square?
T is the sample size. R
Okay.
square is the typical R square
Okay.
that you get from the regression.
All right, sir.
That product TR square should follow chi-square distribution with Q degrees of freedom. Okay.
So basically, we're running a chi-square test on the.
Yes.
Shouldn't we be running a F test for all the way? We're a little
And
confused.
actually, for this, it is not the. Here you have a statistic. Here you have a statistic. That statistic is R squared multiplied by the sample size. This follows chi-square distribution. Okay. So this is the test statistic here. So depending on the calculated value and the tabular value, okay, you confirm the test procedure, right? It's very simple and also kind of routine. Okay. So now, shall I proceed further?
So just give 1 minute, sir.
Yeah. Actually, this discussion is there in Ruth Chase book. Okay.
So can you write the name of the book here?
Author, I think only 2 books I have sent. Ruth Say. Okay. The other book I had sent was, Low McKinley. Campbell Low McKinley. Econometrics of Financial Markets. This is time series analysis of, I think, financial time series analysis. I think that is the title of this book by Ruth Say. Ruth Say is a very wonderful book. Those who are a bit model oriented, you have treasure of information in this book. Okay, highly useful for financial econometricians. Okay, shall I turn it on?
So here the P and the Q could be different, right?
Actually, P general form. This is the general form. So your doubt is why it is P here and why it is Q there. Is that your doubt?
No, I'm saying they could be different. And would the computer model, choose it the length of Q, for example? How is that?
See, for arch test, you make it Q only. Okay. Here when I wrote P, it's a very general form. Okay. So P can be little more compared to Q. Okay. So the purpose of step 1 is to extract the residuals. And once residuals are extracted, and when you square them, when you are doing the regression, adopt this form. But then you choose your Q. Q also choose at a slightly higher level. For example, Q could be 10. Suppose now most coefficients are insignificant. You can reduce Q a little bit. Once you start experimenting, you will learn. But the basic thing is this P and Q, when I symbols, in the first one, the form of the model That is in step 1, in what form you should have the regression for extracting the residuals. In the second, you firm it up to Q. First set it at a slightly higher level, then come down if some of the coefficients are insignificant, like that, right? So now we move to Garch model. It typically, arch model will have only one parameter, that is Q. That is, don't write down, I'm just repeating, okay? So y equals mu plus epsilon t. Epsilon t equals ut sigma t. And conditional variance equation, it all depends on omega plus summation I equal to 1 to q alpha I epsilon t minus I square. So this is conditional variance equation, and the first one is mean equation.
So are we entering Garch right now?
Yeah, now I'm writing Garch. Okay.
All right, sir.
Just to show the contrast, I have repeated the arch process, right? So in arch process, the conditional variance equation depends on the squared lagged errors, lagged innovations. So that is sigma square t minus I. That means sigma square t, that is the conditional variance, it evolves. The volatility style, it evolves because it is time varying. What is the style of variation according to this? According to this. What is this actually? These are all squared innovations in the process YT. Okay. Now, when you generalize this, suppose Q is very large, then you have unnecessarily nuisance parameters. So Q should be chosen such that it should be moderate. You must follow the principle of parsimony. Okay. When there are unnecessary nuisance parameters, then it will not give you the accurate inference. So therefore, a generalization of this has been proposed, in which you have limited number of parameters, okay? But with an additional provision where you will have the feedback from its own past. That means how the current conditional variance depends on its own past, as well as the feedback from the previous shocks. So therefore, conditional variance is expected to draw its variation from two sources. Now in Arch model, what is the source? This is exclusively the source. Whereas in its generalization, you have an additional source. So a typical Garch PQ model is specified as the conditional variance equation equals, this is as it is, plus summation. This term will remain as it is, alpha I sigma t minus I square I, let us say q, plus you will have summation j beta j, okay, sigma square t minus j. Okay, t minus j, and j equals 1 up to p. Is this clear? Look at the contrast between the conditional variance equation of an arch-Q process and a Garch PQ process. PQ process. So therefore, two sources of variation. In this is the additional source of variation for the evolution of the conditional variance. Okay, clear? As usual, epsilon t is assumed to be sigma square t. Okay. In this, same positivity constraints, etc., they apply. So we discuss a very simple case, a case Garch 1-1 model. It is easy to handle. Okay. So in Garch 1-1 model, you will have only alpha and only beta. Of course, omega is already there. Okay. So these are the three parameters. So omega is expected to be small.
So can you just give us 1 minute to write?
Yeah, please write.
Sir, is it possible? Could you explain this second source once again, the feedback loop?
Yeah, I'm coming to that slowly, one by one, because Gach 1-1 model is a very popular model in finance. Okay, and most people who apply this are not very clear about the basics. That's why I make it a point to explain these things in very clear terms. And wherever you have any doubt, please stop me. Okay. So is the taking down over?
Yes, sir.
Yeah. So when it is Garch 1-1, then the conditional variance equation may be specified as sigma square t equals omega plus alpha t minus 1 square plus beta sigma square t minus 1. Okay. So here we have the following parameters. Mu. What is mu? Hello, what is mu?
So the mean is trying to follow
Conditional mean.
conditional mean.
Okay, conditional mean. It is expected to be small. Of course, when you say small, it could be arbitrarily small. Normally, mu is expected to be small, and the positivity constraints apply to omega. That is, omega should be positive, alpha should be positive, and beta also should be positive. The positivity constraints. Further, alpha plus beta,
So could you scroll up just 1 second? So sorry.
yeah, omega positive, alpha positive, beta is a positivity constraint, and mu is expected to be small. Okay.
Yes, sir, got it.
Yeah, alpha plus beta should be less than 1. Okay, but close to unity. But close to unity with usually beta greater than alpha. Remember, beta gives you, okay, how the current conditional variance draws upon its own past. So beta measures that, whereas alpha tells you how the previous shocks influence the current volatility. Okay. Now, the meaning of t minus 1 hat square, the meaning of this is that news about volatility. News about volatility from the previous period. Okay. Then beta hat, it measures persistence. Persistence of volatility. To a shock or impact of old news. Volatility. Okay. Further, the coefficient, this part you can note down if it is. The coefficient measures now alpha plus beta equal is less than 1. That is alpha plus beta is less than 1. Okay. So in a Gauge model, alpha plus beta is less than 1. That is the unconditional variance of epsilon epsilon t is, you have an additional parameter like we have worked out earlier, omega upon 1 minus alpha. This was unconditional variance for arch, whereas unconditional variance for Garch would be additional parameter 1 minus alpha minus beta. This is for Garch. Now, if the Garch equation is slightly rewritten, right, it takes the following form. That is sigma square t.
Sir, can you scroll up for a second?
Yeah, sure.
Thank you, sir.
Yeah.
So could you scroll up? I'm so sorry.
Yeah.
Done, sir. Thank you.
Yeah, okay. So the conditional variance equation may be slightly rewritten as, with some manipulation, alpha t minus 1 square minus sigma square t minus 1 plus alpha plus beta sigma square t minus 1. Okay. It is simply from the previous equation, you make some adjustment. Okay. So here alpha plus 1, here alpha plus 1 measures, sorry, alpha plus beta, this one measures the rate at which the effect dies over time. Effect of what? Effect of the previous volatility on the current volatility. So that is decided by the sum of these two coefficients, alpha plus beta. Okay. Whereas alpha measures the extent, alpha measures the extent to which a volatility shock today feeds through the next period volatility. So that is, this gives you a measure to which the volatility shock today. So if you take the previous shock, how it influences the current shock. If you take the current shock, how it feeds the future shock, that is the next period shock. Okay. So this is the meaning of these two. So when you are modeling a Gauch 1-1 process, look at the sum of the two coefficients, that is alpha and beta. Ensure that the sum will not exceed unity. This is an important clue. Okay. If it exceeds unity, then there is somewhere something has gone wrong. Second is that both should be positive. Alpha should be positive, beta should be positive, and the sum should be close to unity, but should not exceed unity. Okay. So next is a process or a model which we call IGARCH. I stands for integrated. Integrated GARCH. Okay. This word integrated may have been familiar to you. Okay. Let us take a stochastic process which is stationary. What do you call that? It's an I0 process. Am I right? Stationary process. If you say ID process, D not equal to 0, then we say it is, what do you call this as? Non-stationary. Okay. So this non-stationary process are also referred to as integrated process. Integrated process. And similar in the case of Garch process, it is possible that it could be an integrated process. So for that, if alpha plus beta exceeds unity, okay, then the Garch process has to be modified. Okay, but how the modification has to be done? If alpha plus beta exceeds unity, right, then the usual assumption that the sum should be less than unity is violated. So in that case, you may have to modify the conditional variance equation. Okay. So now, suppose they are exactly equal to 1. If alpha plus beta equal to 1, right? So this is an integrated process, like an I1 process. So for this, the conditional variance equation should be omega plus alpha sigma square t minus 1 up to here as usual, plus in the place of beta, you write 1 minus alpha. 1 minus alpha sigma square t minus 1. Okay. So you have packages wherein prima facie this is very close to unity. I mean exactly unity. You have to model this like this, with this as a conditional variance equation. So next class of models, next variant, I must say, is E-Garch, means exponential Garch.
So you're showing us the different Garch models.
Yes, yes.
And could you also give us a use case for these?
See, in certain situations where the volatility process is like, the distinction between a stationary and non-stationary process. What is the essential difference between the two processes? It's a little digression, but to draw some kind of parallelism, I'm bringing this out. Okay. So why do you expect that the process should be stationary, especially from modeling point of view? Because the first two movements are time invariant or they're pretty stable. So that when you estimate a model, On the basis of that, you can predict what the pattern is going to be in future. Whereas if the process is non-stationary, the first two moments are not stable. They vary over time. Then prediction becomes very difficult. And similarly, in the case of an integrated gauge, there is a volatility pattern, and the volatility itself exhibits some kind of shifts, right? So if alpha plus beta equal to 1, right? So that means the volatility process is speeding up, quite, speeding up. So when you want to model that, you will have to appropriately modify the conditional variance equation. Ultimately, we land up with only one parameter. One parameter is sufficient because alpha plus beta equal to 1. Either of them would be sufficient. So that is, since there are a few other models, I'm just, speeding up. As you go along, I think when you start working, estimating the models, you will have more, information on these models. So the next is, the most influential is the exponential gauge, also known as E-gauge in abbreviation form. Okay. So what do these E-gauge models tell us? Okay. So they capture thick tails. Yesterday I was telling, in the case of normal distribution, the tails taper off very smoothly and the curve touches the horizontal axis at infinity or asymptotically. Whereas in the case of thick tails, in finance, I think the thick tails are more common and hence they need a different treatment, especially when stock returns are non-normal, you'll end up with thick returns. So in the presence of such thick returns, what kind of gauge model would capture those things well? So for that purpose, the E-gauge models, they capture the thick tails and also volatility clustering. What do we mean by volatility clustering? It is like this. I'm giving a very simple version of this. Suppose now like this. So these are clusters. A characteristic feature of a volatile series is that there exists clustering. Clusters are there. Okay. So what is the significance of these clusters? Suppose now I'll take this case. This is the mean level. This is the mean level. They go above the mean level. Having gone there, it sticks for some time. Then the investors expect that the prices could follow anytime. At the same time, they wouldn't hurry up. So then one fine morning, it will slip, fall. And after falling, this will continue for some time because they're very sticky. They cluster here around this time. Again, after some time, the market expects that it would rise. And having risen, it stays for some time. This is called clustering, volatility clustering. Okay. So to capture thick tails and volatility clustering, okay, then this E-gauge models are proposed. Okay. So these EGARCH models may not capture what is known as the leverage effect. Leverage effect. What is leverage effect? What is leverage actually? In financial markets, what is the meaning of leverage? Hello?
Usually, it has it has something to do with borrowing.
Okay. But when it comes to price changes or returns, suppose, there is a negative shock in the market, then what will happen to the returns? Will it not pull down the market? Negative returns pull down faster than positive returns, stimulating the market. So there is some kind of asymmetry because gains in the market, if there are gains, they influence the market slowly, but losses may have a powerful effect in pulling down. So this is actually the leverage in our present context. So basically in EGARCH models, okay, you have some versions. So one version, depending on the model, you have a modified conditional variance equation, right? So one version of the EGARCH model has been given by Nelson. This is also a popular model. Nelson, 1991. Okay. He proposed EGARCH 1.1. So according to him, what works better is a conditional variance of this kind where omega as it is beta ln sigma square t minus 1 plus alpha flower bracket epsilon t minus 1. This is modulus t minus 1 multiplied by sigma t minus 1 minus 2 upon pi square root plus delta epsilon t minus 1 upon, this is upon, divided by sigma t minus 1. So this is the conditional variance equation he tried out. Okay. So according to this, there is no need to impose restrictions except that beta modulus of beta should be less than 1. Okay. But what is the advantage of this? The advantage of this is that sigma square t will reflect non-symmetric. See, this volatility asymmetry can be captured with the help of this model. Actually, volatility asymmetry, as I just said, when there is a negative shock, the market is pulled down. Positive shock, it pulls up, but not as much as the negative shock pulling down. So this kind of asymmetry, okay? So the parameter delta will give you the measure of asymmetry, okay? Then, of course, this is just for your quick, reference, I'm giving all these models, but up to Garch 1.1, if you are thorough, that will be sufficient. Let me introduce a few more models very quickly. So for leverage effect, the conditional variance, actually this is proposed by somewhat old French et al. Form of French, the same French. They have proposed this in 1987. Okay. So the conditional variance, because all the models they vary in respect of specifying the conditional variance equations. Omega plus beta ln sigma square t minus 1 plus alpha into epsilon t minus 1 upon sigma t minus 1 plus gamma epsilon t minus 1 upon. Here, please read this as modulus. Sorry, I'm doing it in a very clumsy way. Read this not as bracket, but as modulus. Okay, modulus. So, what is the additional parameter that you have introduced is gamma. So, our focus should be more on gamma. If gamma is negative, the leverage effect is present. If gamma is not equal to 0, the impact is asymmetric. If gamma is less than 0, please note, the leverage effect is present. So when do you say that it?
So could you please, I'm not, let me just, so in this effect, what is happening is that the downward effect is impacting it more than the upward effect, right?
No, actually, when gamma is negative, see
So
here,
okay, sir.
when gamma is negative, from this you cannot guess. Only when you estimate, if the coefficient is negative, then it's a confirmation that there is a leverage effect. Okay. What is the leverage effect? That is asymmetry. Okay. Negative shock influences more compared to the positive shocks. Suppose now the coefficient is not equal to 0. Okay. Then it reflects some kind of asymmetry. Suppose when gamma is less than 0, that is also asymmetry, but it is negative. But simply if it is negative or positive, but it is not equal to 0, it simply tells you that there is asymmetry in the process. Next model, most important model, is another version of asymmetry. This is a very popular model. All of you should try to GJR model. This GJR stands for Glaston, Jagannathan, and Runkel. I think Runkel and Glaston must be familiar to you already in your financial, economics literature models, etc. So the conditional variance here, equation here is that sigma square t equals, okay, is specified as alpha 0 plus beta 1 sigma square t minus 1 plus alpha 1 epsilon square t minus 1 plus alpha 2 multiplied by I t minus 1. This is important. Here alpha 1 sigma square t minus 1. Here also sigma square t minus 1 is there. But the coefficient alpha 2 is different because this is being multiplied by it minus 1, which is an index. So it minus 1 is defined as, it's a dummy variable equal to 1 if epsilon t minus 1 is positive. That is positive shock or good news. Okay. Otherwise, 0 if epsilon t minus 1 less than 0. That is bad news. Okay. I think this is a pretty simple kind of model wherein the volatility asymmetry can be gauged through. Of course, the non-negativity conditions, that is beta alpha 0, beta 1, alpha 2, should be satisfied. Okay, that is all the parameters are positive. Okay, suppose if alpha 2 is negative, then the leverage effect is present. Actually, those interested may work with Stata, software Stata. Okay, all these models are there. All that you need to do is to feed your data and experiment with all these models. Then I will introduce another T gauge. T stands for threshold gauge. Threshold gauge. Okay. So this is proposed by Jacobian, 1994. Okay. This is similar to the GJR model. Similar to GJR model. Okay. So the conditional variance equation of this is as follows. Sigma square t equals omega plus I equals 1 to q alpha I sigma square t minus I plus summation j equal to 1 to p beta j sigma square t minus j plus an additional term gamma sigma square t minus 1 d t minus 1, and d is index number, an index here. Okay, as defined earlier in the previous one, if dt equal to 1, if epsilon t is negative, equal to 0, otherwise. So that means this is bad news and this is good news. So good news has an impact. Good news has an impact of alpha, while bad news has an impact of alpha plus gamma. If gamma is positive, then leverage effect exists and bad news increases volatility. While if gamma is not equal to 0, the news impact is asymmetric. This is there in Ruth Chase book. You don't need to worry if you are not able to capture this. Then two more very simple but highly useful models are Garchin M, Garchin mean. Is known as Garch M, to be pronounced as Garch in mean. Okay. So what is the basic underlying theory? Okay. The logic is that there is increase in variance resulting from higher expected returns. So this is drawn from the risk return trade-off. Okay. So when risk is more, then expected return will also be more, right? So this idea is built into the mean equation. How, of course, this can be done in a variety of ways. But in Garchinian standard formulation, yt equals mu, that is the conditional mean. In addition, you have a parameter beta 2 sigma square t plus epsilon t. And sigma square t is, as usual, you have the Garch process, omega plus alpha sigma t minus 1 square plus beta 1 sigma square t minus 1. Look at this a bit carefully. Okay. Here, the impact of the previous volatility and the current volatility is given by beta 1. Whereas beta 2 tells you that the current volatility, if current volatility is high, then the return should also be high. So therefore the average return should be high in the presence of high risk or high volatility. So that idea is built into the mean equation. Whereas this term, in all the models that we have discussed, symmetric or asymmetric, this idea is not incorporated. But in Garch and mean process, okay, there is a feedback that is from the conditional variance equation, right? There is a connection to the mean equation itself. And what is the basis for this? Higher expected return means higher risk. So that means increased volatility results in higher expected return, and that is captured here in the mean equation. If beta 2 is positive, if this coefficient is positive and significant, then increased risk leads to a rise in the mean return. That is the implication of this. Okay. So beta 2 sigma square t, that is this, the product of these two, this particular term is interpreted as risk premium. risk premium. Another version of Garch in mean model is very interesting. That is, the relationship between mean of a return and its variance, they both are accommodated in this fashion. Yt equals some theta xt plus psi t plus epsilon t, and sigma square t as usual, omega plus alpha t minus 1 square plus beta sigma square t minus 1. Actually, what is this? In what way the previous formulation is different from this? If you look at the previous formulation, it is beta 2 sigma square t, right? But here, in addition, something like this is here. In addition, there is an exogenous term, that is xt. And what is that xt here? It means the relationship between the mean of a return and its variance. So this term is the mean of a return. Earlier we used to write this as simply mu. Okay. So the mean of the return and its volatility, that means its variance. So these two are incorporated. That means mean itself is not constant, but it varies. What is the style of varying? That is given by the parameter theta. So both the ideas, that is mean of the return and variance, they're related, and these two are incorporated in the mean equation. And the last model that we are discussing today is arch in mean. Earlier, what we discussed was Garch in mean, abbreviated as, okay. So the mean equation is Yt equals some symbol P sigma square T plus epsilon T and sigma square T omega plus alpha sigma square T minus 1. Of course, this is a very simple version. There are also versions like Yt equals some phi of omega plus alpha sigma square T minus 1 plus epsilon T. All that is done here is that this sigma square is as well put it in this, in the conditional variance equation. I think that should be given a full coverage of these Archie-Garch models.
So could you scroll up 1 second, please?
Yeah. This is the usual familiar conditional variance, and the only change in this, in the arch process, which used to be simply Yt equals mu plus epsilon. In the place of mu, you have this. What is this actually? This you are introducing the volatility here itself. If volatility is high, expected return is also high, and that is incorporated in the mean. So the mean expected return also varies according to the volatility. That is the idea. That is in the mean equation, that modification is made. Okay. And the last point, power gauge. At the idea level, I thought I should tell you this. Abbreviation form PRH or P gauge. Okay. If you look at the conditional variance equations, okay, across the models, you have a variety of equations. For arch process, for gauge, for eye gauge, E gauge, again various versions, GJR, Jacobian, okay, Nelson, all these, so many versions are there. If you trace the functional form of all these models, etc., you always focus on sigma square. What is sigma square? Sigma square t. What is this? Conditional variance. Conditional variance. Conditional variance is also variance. Okay? And variance is nothing but the second moment. Second moment. Okay? Here the issue is, why always the volatility phenomenon should be measured in conformity with the second moment? Why not a higher order of moments? Okay? Why not the functional form of the conditional variance equation be completely left to the data rather than conforming to these forms which are a priori arbitrarily imposed on the model? Actually, this is the basic idea. I don't know whether you are catching this or not. Instead of, for example, sigma square t, writing like this, summation alpha I t minus I square is summation beta j sigma square t minus j. Okay. Why not sigma t square theta equals omega plus summation alpha I theta plus why not like this? Okay. If theta equal to 2, fine. It will conform to the whole lot of conditional variance models. What if it is not? Suppose theta equal to 0.7, and the conditional variance equation will have a totally different look. And the volatility patterns that could emerge out of an estimated conditional variance equation would be entirely different. So here basically the idea is that you estimate a general class of models, a parametric class of models. Depending on the value that the parameter is assigned, you have the whole lot of conditional variance equation models as particular cases. Why always emphasize on a particular case? Why not go for a general case, a case which data determines? Data determines the form rather than you specifying based on a single moment called the second moment. Is this idea interesting? Hello? It questions the very formulation, the very basis of the whole class of these models. Okay? Why the second moment based analysis? Why not leave the functional form to the data itself? It's a wonderful idea, okay? But it is slightly at the higher level, okay? You have any questions? Now, what
No,
is
sir. Just could you scroll up twice? A little bit more, sir, to the where power guard starts. Yes, sir. Just 1 second, sir.
Yeah, please.
And sir, could you scroll down to the next part once? Thank you, sir.
Welcome. So, those interested may also read another strand, stochastic volatility. Okay, I will give you in few minutes the whole idea. Okay, you have the conditional variance equation, yt equal to mu plus epsilon t. Okay, epsilon t equals, right, ut and sigma t, and sigma square t. We have the conditional variance equation because we have variety of these models. Now, in stochastic volatility, two things you have to note in the volatility analysis. The conditional variance equations in the models that we discussed, they are deterministic. Sure. They are deterministic. For example, sigma square t equals omega plus alpha t minus 1 plus beta sigma square t minus 1. If you observe this, what is the nature of this? Is this stochastic? Meaning, is it a random variable or whether it is deterministic? What is your view?
So it's just stochastic.
Huh?
Sir, even I feel stochastic, sir.
Okay. Is there anyone who feels the other way in the class?
It's conditional based on the previous volatility
Yeah. That is
and
fine.
determined by the two coefficients.
Yes. So therefore,
Maybe deterministic you can call it.
Huh?
You can call it deterministic.
Yes, you are right. It is deterministic. Okay? Because there is no role for any stochastic element. There is no role for any random factor. How is sigma square t is visualized here? It is purely visualized in terms of changes in sigma square t minus 1 in this case, and also the previous volatility, that is, epsilon t square minus 1, that is this and this. Is there any possibility that some random factor, right, like influencing sigma square t? Is there any random variable, something like this? No. In all the models that we conditional variance equations we have specified, is there any such phenomenon? No. So therefore, the conditional variance equation is deterministic. It evolves in a deterministic fashion. You are 100% able to determine that. Determine within the narrow confines of your own formulation. You are not leaving any chance to any other factors. So therefore it is deterministic but not stochastic. Later, if someone asks you this question in any presentation or in any interview, be sure to say that it is deterministic, not stochastic. Okay? Right? Now, the class of stochastic volatility models differ in one important sense. Structure is the same. Ut, sigma t, and sigma square t is
So
yeah.
can we do this model tomorrow? Because I think after doing so many models, most of us are like a little
No,
saturated.
I'm not doing any. I'm just giving the idea and leaving it.
Okay, sir.
I'm not straining you any further. So in stochastic volatility models, the sigma t, okay, which is deterministic here, okay, because sigma square t is deterministic, therefore sigma t is also deterministic. It is viewed as some function of eta t, okay. That is how it becomes stochastic. So volatility viewed in this framework, all the models, they are in the realm of stochastic volatility models because the conditional variance is formulated to be stochastic. Why it is stochastic? Because the sigma square t is determined by a stochastic element eta t. Okay, in this sense it is stochastic. What is the complication here? You already have one error here, another error here, and another error here. Okay, this is a very simple error, but then you have one unknown and two errors which are unknowns. That is the complication here. What is the advantage? The advantage is that something which cannot be determined 100%, something which cannot be determined 100%, okay, you are able to take the help of some chance elements. That is the advantage of this, okay. Anyway, so those interested may pursue this. In Ruth's book, this discussion is there. Now, what is left out for us following the syllabi, etc., are two things. Most importantly, the CAPM model. I would like to do it like I have done volatility in a very detailed and critical way. But I don't know when you will be able to find time. Okay. So, hello. It all left to your response. If all of you are interested, I can continue it. Hello?
Yes, sir. We are still here.
Yeah. So tell me when you think, but tomorrow I may have some other work. Any time other than tomorrow. Day after would be fine.
Yes, sir, it should be fine.
Yes,
Yeah.
sir.
Yeah. Yeah. Please coordinate that and communicate the timing along with the Zoom link.
So would 2:30 day after work for you?
Yeah, should be fine, I think.
So I'll inform Shrikant, sir.
Yeah, please. Okay. Right. Any questions on today's thing?
Sir, I have a basic question.
Yeah, please.
Sorry for
No,
going
please.
so basic. It's like, when we looked at, just take this equation, your epsilon t and sigma t, they are directly related.
They are. No, they
You're deriving epsilon t from sigma.
epsilon t from sigma.
In which case, bringing in a separate coefficient, let's say beta, in addition to the alpha, was what is confusing me. So the feedback seems to be double, or I'm not getting it properly, perhaps.
Okay. What is epsilon t? Yeah. You please follow it up. What is epsilon t to the extent that you have understood? It is an innovation in YT.
Yeah, this is the volatility around the mean.
Yeah. Yes. Actually, YT, let us say if it is returned. Okay. So the return process has a mean level. And what is that mean level? Conditional upon the previous information, that is mu. This is constant. Okay. In addition to that, the return process is also subject to a shock, that is epsilon t. And this is innovation in YT. It's called, in technical words, innovation in YT, right? But this innovation in YT, which is a random phenomenon, right, has two components in a multiplicative way. One component is another random variable ut, which has mean 0 and variance unity, rather a standard normal variate. In addition, right, this is driven by a volatility process, and that volatility process is your sigma t, right? So this, which is not stochastic. Epsilon t is stochastic, and you are relating stochastic with another stochastic, that is ut, and supplementing this ut by a deterministic process sigma t. That means how volatility evolves. If there is a higher level of volatility, right? So this will influence the return process via epsilon t. Since epsilon t is random, you will have to make it random by introducing ut. So that is how this is formulated. That is the basis for this. Okay. Now you please ask your question again, if I could.
My query was, sir, how do you differentiate between alpha and beta in the Garch formulation?
You mean in the conditional variance equation?
Yes, in the conditional variance equation.
Yeah.
When you say sigma square t is alpha times epsilon t minus 1 and beta times variance t minus 1.
Yeah. Let us take this as the standard thing to clarify your doubt. Okay.
Yes.
So you want to know what is alpha and what is beta. And how do you distinguish these two? Is that your doubt?
That's right. And because from the formulation, it looks like alpha is already including the beta element, because epsilon is already including the sigma.
No. It's not like that. See, in this, what is that we are trying to explain? we are explaining a process for volatility. Okay, that means volatility is evolving in a volatile fashion, right? In its evolution, which is a deterministic evolution, there are two components that contribute to that. Okay, one that contributes is the previous shocks. The previous shocks are represented by the squared previous shocks, because the volatility here you are considering variance. So this is one source, how the previous shocks contribute to current volatility. That means how previous shocks feed on to the current volatility. That is one source. And a measure of that is given by alpha from the previous shocks. Then coming to beta, right? We are visualizing that the current volatility is also influenced by its own previous level, and beta measures that. So one measures its own level, the other one measures the shocks. So therefore alpha and beta can be distinguished in this fashion. They have their own independent source of variation contributing to volatility. Okay.
Okay, sir. Let me read up some more, because I'm not actually a maths oriented
No,
person.
no, it is all
I'm
pure.
trying to understand it intuitively.
Okay, yeah, I think that is more important. More than the symbols, intuition
Exactly,
is
because
very important.
then the computer will do the calculation. That's not the.
Yeah, I think intuition is very powerful.
So one more question I had. Anyway, I
Yeah.
think only two of us are there on the call now. If you are free,
Okay.
I can ask.
Yeah, sure. Please go ahead.
Yeah. So, sir, I'm a retired finance professional.
Okay.
Okay. I just joined Gokhale for a PhD.
Okay.
My area I want to pursue is monetary policy.
Good. Very good.
Because I had some, practical experience in that field. I was a treasurer and, dealt in government securities and all that, foreign exchange.
Great. Yeah.
So practical point of view, I want to bring some practical elements to the research and stuff like that.
Mm.
And when of course, I have not started looking at the,
Literature.
the literature as yet, because the literature is full of, quanti data and modeling, which I'm not very. I mean, I can barely understand, but it's really full of that. That's why I joined this, course. Professor Reddy has recommended that I join your classes.
Okay. Good.
So now I mean, of course, because of this, I went and learned some matrix algebra and integration. So now I'm in a better position. I'll start perhaps looking at the literature now after 6 months.
Okay.
Now my query here is, when I look at monetary kind of data, so this more like where or DSG models will be more applicable, right, than Arch or Garch. These will be more for financial, like stocks or financial data.
Yeah, actually, wherever things are changing very fast, these arch models may have some relevance. But let us say monetary aggregates or interest rates or monetary policy decisions, they don't change so quickly or so fast. So the element of volatility is very minimal there. So therefore, the use of models of this kind, may not be contextual.
Right.
Yeah. Yes.
Okay,
But
sir.
nevertheless, knowing these things is always good.
Yeah. So I mean, it gives more confidence in
Yeah. For example, forex reserve levels. If you treat it as a random variable, then some of these models can.
Like in parallel. I think you have done some research on monetary policy. I've come across a couple of your articles.
Yeah, long way. I think, in fact, I started with that.
Okay. Yeah.
Yeah.
So you're in Hyderabad, sir.
Yes, Hyderabad.
Okay, I'm also originally from Andhra Pradesh. I've been in
Okay.
Bombay all along.
Okay.
So
Yeah, when you come this side, please drop in.
I'll do
We will
that, sir,
meet.
definitely.
Yeah.
You're in which university, sir?
University of Hyderabad.
You're in University of Great. I've been working in Bombay in finance all along. I've
Okay.
also worked with Reserve Bank for a decade.
Okay.
Now retired, settled in Pune.
Okay, good.
I was a long time back Gokhale student.
Okay.
Okay.
Very nice.
So one thing, sir, one thing I wanted to ask you. When I look at inflation data, it seemed to just follow any of these ARIMA or whatever models you can seem to easily fit there. In which case, how does that really policy implications of trying to influence something which has its own life? It seems to follow its own cycles.
Yeah. Yes. Yeah, there is some literature on the cyclical component in.
Yes, sir.
You can check whether there are some unit roots.
Right, sir.
Whether there is a unit root in. See, in price data, there could be a unit root, but not in inflation data. Inflation rates are fairly stable, while the prices could fluctuate a bit more.
Right.
Yeah.
Right, sir.
So nice. You can send a mail to me.
I'll
Dr.
do it,
Reddy
sir.
has my number.
Yeah, I'll get your number and
Yeah,
stay in touch with you, sir.
sure.
Thanks a lot. Thank you. Thanks for the
All the
extra time.
best. All the
Yeah.
best.
Yeah.
Okay, bye.
Have a good day, sir. Bye.
Thank you.